Hello, good morning. Sorry for that delay. 13 of us, I think, since 26 student class, so we're losing all. Oh, there's one point I'm noticing. I do record this and I put it on YouTube, and YouTube shows this number of views, right? And I noticed that it is hardly viewed. Like sometimes you have about 2 views or something. So the question is this really needed? Or how about this? How many of you would like to have a recording? So that's good number. So I'll keep doing this. So this is good to have it, even though the number of views has probably later on it shows up. Okay, that's okay. Okay, the homework 4 due. Wednesday, and 2 is on the Friday before spring. And most of the advice and suggestions for what we do for midterm, everything remains the same. Now that you've taken a midterm one, you have a rough idea of what to expect. Any general comments or questions? Anyone else at this stage? Okay. Let's keep working on the idea of a new type of force we have introduced. It is called the electric force. The law itself is called Coulomb's law. It describes the force exerted by one electric charge on another electric charge. And the question comes, where do you see electric charges? It comes in positive or negative. And let me put this as a question. Suppose you want to charge an object. What would you do? How would you go about charging an object? Usually, most of us are neutral, right? But if you have to create a positively charged sphere, which is what we talk about here, how do you go about doing that? Intuitively, anything? Yes.
You rub it against something?
Yes, you just rub it against something, and that is all that is needed. And whenever in winter you remove your sweaters, it is more common in woolen objects. What is happening is that you're rubbing your body against the sweater, and there is a charge imbalance. Some of the charge, it could be positive or negative depending on the material. That goes from one to the other, and one gets positively charged and the other gets negatively charged. So that's good thing to realize, that how do you create this positive charges. And the moment you have a positively charged object, so let's we are going to introduce the idea of electric potential, okay? Very closely related to energy. So the idea is that we introduce the idea of electric force, and now we want to have an idea of what is electric energy. We defined what is electric potential energy last time. So let's talk about electric potential now. But before that, let me review whatever we did last time. So let's have a positively charged sphere. How would you create this? You just rub a sphere against another object, and if you rub it against the appropriate object, then it will be positive, and otherwise it will be negative. Certain objects have a tendency to lose electrons rather than gain electrons. We know that the electric field associated with it is described by radial lines if it is a symmetric sphere. That's a electric field lines associated with this positive charge. So that's E. And it is radial. That means this vector, this symbol represents that it is radially outward, and its magnitude is K, Q over how far you are from it. So if you go farther and farther, R becomes larger and larger, something in the denominator, a large number in the denominator makes the electric field very small. This is also interpreted as force per unit charge. Per unit charge. If you think of this as 1, that means this is charge Q1. So that's charge Q1. So this is the electric field created by the charge Q1, and this will be the force exerted on another charge. A charge cannot exert a force on itself. So you bring in another charge here. This is the measure of how much force it will exert on that particular charge. So let's pretend that there is this charge Q2 here. So that's your, let's say it's positive. So that's charge Q2. Since the force, since it is experiencing a force, we can interpret this idea in terms of energy instead of talking about force. How much is the change in energy between the object being here or it being moved? So what is, so this leads to the idea of what is force. Another interpretation of force in terms of energy is that force is a manifestation of the system trying to reduce the energy. And that's a much stronger statement. Anything that you see around you, if you want to have a physical understanding of it, one basic thing we have realized, whether it is physics, chemistry, almost everything that you see around you, it is an energy that the system is trying to minimize. By system, I mean the nature. Think of a hot cup getting cold. It is because its energy gets reduced. Think of when you drop an object, it goes down. That's because it is trying to reduce its energy. It is an energy that the system is trying to reduce, and in that process, it seems like there is a force acting on it. It can be understood as there is a force acting on the system, and the object is moving in due to that force. Same idea here, and now we want to talk about in terms of energy. There is a force, of course, here, but let's think of energy. Where is it maximum? Is it larger in this direction, or is it larger in that direction? The system will try to go towards the direction in which the energy is lower. So what is the energy? So we introduce the idea of electric potential energy. So that's electric potential energy. And that is simply K Q1, Q2 over R. The only difference between a force and an energy is that there is one less distance. So dimensionally speaking, this is 1 over R. Force was 1 over R square, right? Electric field, multiply it with charge, and there is a 1 over R square. So that's a primary difference between the, and of course it's not a vector, right? That is a vector in the sense force is always in a direction. In which direction is it going to tend to move? That's the idea of a force. So interaction energy is given by K Q1 Q2 over R square. If we keep Q1 and Q2 the same, if we are talking about the same charge, it is clear that U will be smaller as you go farther, right? R, if you were to increase, R will increase in the denominator, so it's larger. Oh, sorry, R larger means energy smaller as you go away. So in this direction, this is small, and in this direction, it's large. Right? We are talking about energy here. Energy is large when it goes towards the Q1, and it is small when it goes away from Q1. That means to say that the system will try to do that. Wherever it is small, that's all the system tries to do. In fact, you can explain anything that you see around yourself whenever you don't have any equations and the physical principles governing a system is not completely well known. And if you can talk about energy, it'll always try to minimize the energy. That means to say this charge will actually move in that direction. And that's what we understand by a force, right? Q2 will move towards that direction. So a system will always try to minimize its energy. There is one catch here. If by any chance this was negative charge, right, then it is slightly different because now it's a negative number. If one of these is negatively charged, then this is a negative number, and a larger negative number is not necessarily smaller, right? Because on a number scale, so if you have a number scale, so that's 0, then you have 3, and you have 30, then this is of course larger, and what am I saying? Yeah, sorry. So this is -3, and that's -30. If the system is trying to reduce its energy, it tries to go this side. So 3 is less than 30, but -30 is less than 3. So if you're negatively charged, you tend to go this way, and you have positive interaction energy, then you go this way. Either way, along the number line, it is in the same direction, but this formula you should be careful. In fact, here, when you look at it, if it was a negatively charged particle, as you go closer, R actually is getting smaller. That means this number is getting larger, but it's a negative number. So in fact, it is smaller. So you have to take care of that negative sign in there. So that's a little inconvenience in there as to energy has to be interpreted as are you interacting with a positive charge or a negative charge? So you try to come up with a concept that is independent of that second charge. Exactly like electric field, force is a property of two charges, but electric field is a property of a single charge. So you remove the second charge. You want to do the same idea here. So now we call V. So this is slightly different from U. So this will be called electric potential. Very closely, or the words are very similar, but except that there is no word energy. So V is electric potential, U is electric potential energy. Very similar words, so be careful that there are two independent concepts. V is the interaction energy per unit charge. Let's take out Q2, right? And let's call that V1. In fact, you can call this U12. This is interaction energy between 1 and 2. But now this is a property of 1 alone, and that's equal to K times Q1 over R. And now you notice, so the idea remains the same. This is still the energy, but now you're talking about energy per unit charge. And again, I forgot to move it from there to here. Okay. So electric potential is the energy per unit charge. When it is per unit charge, you can ignore this positive charge. In fact, we are always talking in terms of positive charge. if you want to think of it as a negative charge, you have to add a negative sign to that. All the features remain the same. But whenever we are talking about electric potential, you have taken out the other charge, so that issue about the second charge being positive or negative is not relevant. It still is important that this could be negative charge, and in that case, you tend to get closer, or the electric potential tends to be larger, closer to that. So let's again talk about electric potential alone without having defined that. Let's say electric potential due to a point charge, same idea. So that's your positively charged Q, that's positively charged, and we have the electric field lines going this way. And let's again ask, what is the value of the electric potential at a closer point? So that's larger, but once R is the same, it is the same everywhere here. So this point is on the surface. V remains same. Like it doesn't matter whether I'm at this point or at this point, they are all at the same distance because it's a radius of a sphere. So electric potential remains the same on this particular sphere. That's an abstract sphere, there is nothing on there. But if I were to bring in a positive charge and move it here, it doesn't change its energy. That means to say that it will not tend to go that side. A positive charge, if you bring it next to another charge, it never tries to go perpendicular to that. It always tries to go towards it or away from it, especially if it is at rest, and it will never go in the perpendicular direction. These points where the electric potential energy is the same for an external charge is called an equipotential surface. That's an equipotential surface. Clearly, there is a surface of equal electric potential. If I were to go farther, it will get smaller. So there is another equipotential surface here. And I can keep drawing equipotential surfaces and they will be concentric spheres. It's not very hard to see that. And also notice these surfaces seems to be always perpendicular to the force, which makes sense because they don't, if they're equipotential, they will never try to go in that direction, which means that there will never be a force in that direction. If they try to go in that direction, or if there is a tendency for them to go in that direction, that means there could be a force acting on it, but there is no force acting on it perpendicularly. So force is always perpendicular to an equipotential surface where force is related to electric field. So electric field lines are always perpendicular to the equipotential surfaces. So that leads to a very clear idea of drawing equipotential surfaces. Once you know how to draw the electric field lines at each point, make them perpendicular. And these are surfaces. Whenever you have a line, there is a whole surface that can be perpendicular to that. So find surfaces that are perpendicular to electric field lines, and that's your equipotential surfacing. Here, this is a higher V, or I should say this is lower V. By that I mean lower electric potential. That's a higher electric potential. If there is a higher and a lower electric potential, that means I can talk about a potential difference between these 2 points. So let me say this is point A, and that's point B. And I can talk about a potential difference between those 2 points. I should move this. So this leads to the idea of electric potential difference. And let's say delta V changed in potential. Whenever I say capital delta, that means change in potential difference. So that's VA minus VB. It could be any 2 points for this particular system. If I choose my VA and VB, that's my potential difference. So that, what is that equal to? That's K times Q over R, the distance from the center when you are at point A, minus K times Q times distance when you are at point B. So let's do a simple calculation for a given charge, and the distance is given to us just to have a feel for how much this could be. So let's say Q is equal to, let's say, 1 microcoulomb, and the distances are A. So let's say this is a large sphere of 10 centimeter, you go to 20 centimeter, and then you go to 30 centimeters. Let's say. So that's 20, let's say 25 centimeters, and our B is, let's say, 50 centimeters. So you immediately put in the numbers. So that's 9.0 into 10 raised to 9 times 1.0 into 10 raised to minus 6 divided by, this is 0.25. Work in meters, and the number here will be exactly, so if I multiply by 2 here, 2 on the top, I get pretty much the same number. So this is 1 by 2 times the same number here. So let's calculate this. Where is my calculator? That's 36,000 minus half of 36,000, because it's the same number here, right? So that's 36,000 here, because if I multiply by or rather 50, that can be written as 2 times 0.25. So if you put in the numbers there, it will come out exactly the same. So that's 18,000. Which is 18,000. Now we have to write a unit for this. We said it is electric potential is energy per unit charge. Energy is measured in joules and charge is in coulombs. So that's joules per coulomb. That's perfectly fine, but electric potential difference or electric potential is such a common concept that will keep coming in the next few chapters that you create a vocabulary for it, and you have the letter V for it, or volt. So this is a joule per coulomb. It's basically volt. So that's 18,000 volt. And you would notice that this volt is nothing but what we use in our terminology when you're plugging it into wall sockets, or when you're using batteries or cells. You say 9-volt battery. Here it is a 110-volt outlet, and that's exactly the same concept. So what do we mean by that? Whenever you think of a battery, there are 2 terminals. Whenever we think of a wall socket, there are two points where you put it in. In fact, sometimes there are three, but the third one is mainly for safety. That's called an earthing wire. But there are always two terminals. That's when you say this 110 volt, that's the potential difference between those 2 points. Somewhere those 2 points are going and connecting to put 2 points which are at high and low potential. That's what your power lines are doing. They take you to a point where there is one is at a higher potential, one is at a lower potential, so that you can use that energy for running your devices. So the main idea is to have a potential difference. You can create it by mechanical ways or using by burning fuel or running water. Any way you can create a potential difference, but you want to convert it into electric potential difference. So you want to convert it somewhere where you use the water running through a river to charge it. How will you charge this? You'll run a motor, right? You want to rub things around. So you will make the water go through a motor which will rub things into a charged surface, and it will create a charged sphere. And once you have created a charged sphere, you have a potential difference between 2 points. That's a very rudimentary way of creating a charge difference. There are a lot more efficient ways, very efficient ways. Converting into electric energy is one of the most efficient energy. That's why you will hear that electric energy is much more cleaner than other forms of energy, because once you have electric energy, how you convert it into mechanical energy is very efficient. That means about more than 90% of the electric energy can be got as you're running for running your device. But what is usually lost is that to create electric energy, most often you're using some other form of energy. For example, it could be coal, and that's not at all really efficient, and that's not clean either. So one should be very careful in making this judgment as to what is to be done. But having said that, we are talking about potential difference, and once we have this idea, we will take this on and start working with electric circuits. But it's the same idea. Electric potential difference is what is needed for a charge to go from one point to the other point. Here, since this is at a higher potential, if you keep a positive charge here, its tendency is to go to this point or this point. It will go here, but these two are at the same point. Let me, while we are on this, let me draw the electric potential line or equipotential lines for a negatively charged sphere also. So if you have negatively charged sphere, here the only difference is that now the electric fields are going in. The tendency for the charges is to go in. Remember, tendency represents going towards lower energy. So that's your electric field lines. Negative charges are sinks for electric field lines. And now you want to talk about equipotential surfaces. It's again the same. It's perpendicular to this field lines, with the significant difference that when you're closer, it is actually smaller electric potential. So that's your equipotential surfaces, perpendicular to the lines. This is higher V, and this is lower V. One can use exactly the same numbers. Instead of saying this is a positive charge, make it a negative charge, and you will see that this will change sign, that will change sign, this will make it minus 18,000 volts, which means that VA is larger than VB. So that's the basic idea. But now we can also extend this concept immediately to more than one charge. So I talked about one sphere, two spheres. So how about there are more than one charges? So let's say multiple charges. So let's have a situation where you have a positive charge here. It forms a cube, let's say that's a negative charge. And that's a negative charge again, and that's a positive charge. Let's say they are all the same magnitude, that is, this is negative q, the q remains the same, that's positive q, that's negative q, and that's positive q. We have earlier talked about what is the electric field at the center, or I can talk about electric field at this point, or any point I can talk about electric field, which will be a measure of how much force a charge will experience. But now we can talk about electric potential at any point. At any point in space, which is an observation point, I can talk about the electric potential. So let's say this is the center. So let me call this point A. So the question is, what is the electric potential? Electric potential at point A. And then we'll talk about energy using this idea, which will clarify as to how is electric potential related to potential energy. So what is the electric potential at point A? Let's have Q is given, let's say Q is 1 microcoulomb, and let's say the length L is let's say 50 centimeters. Right, so those 2 points are given to us. So let's calculate the electric potential at point A. Notice that electric potential is a scalar quantity. It is not a vector, so I don't have to add like vectors. So it is significantly easier. So it is the, let me call it 1, 2, 3, 4. So this is the electric potential at point A due to 1. This is the electric potential at point 2 due to at point A due to point 2 from the charge 2. So that's 2 of them, third one and the fourth one. So basically I'm trying to say that they all add up. They all add up like numbers 1, 2, 3, and 4. So this is equal to K times plus. So it is K times Q divided by, what's the distance in here? So let's say that's a distance X. But that we can calculate, because if this is X, that's your L, that's also X. This is a square. And if this is length L, that's length L. And this is a diagonal element. And this is 45 degrees. And that will be 90 degrees. So that's a right triangle. So that immediately tells me that x squared plus x squared is equal to L squared. That means 2 times x squared is equal to L squared. So x is equal to, divide it out, so it is L over root 2. So here, this is 50 over root 2. Let me write that as L over root 2 itself. In the next slide, I'll put it the numbers, but you will see that before that there will be some cancellations happening. So, so that's about x, but once we have the x, this is the electric potential due to this. It is positive. That means to say that relative to this, this has a positive energy. If you had to have a positive charge, the tendency for this is to move away. So if you put a positive charge here, it will experience a force away from it. Negative, the second charge is negative. That's minus K times Q. It's the same length, right? It's the same length X here because it's a square, and that X is L over root 2. Oh, we should move this again. And third one is positive. That's KQ over L over root 2. And the fourth one is negative. That's very nice because even before I put in the numbers, it is clear that there is a positive number coming, negative, positive, negative. And if they are all the same charges, we said they are all 4 identical charges except for one, 2 of them being positive and 2 of them being negative, they all cancel out. Right? So even though they are positive and negative, the electric potential at this point is exactly 0. That's interesting. So what can you conclude about that? So let's have this point A. And now there is another point where things go, where the electric potential is 0, which is an obvious point, and that is at a very large distance. If you go very far away from these 4 charges, these distances R becomes larger and larger. What is the electric potential? The electric potential due to 1 point charge is KQ over the distance from the observation point. So if you are at a very large distance, imagine infinity, each of this charge is at a very large distance. So the electric potential due to each one is 0. So at a very large distance, it is 0. And at this point, also it is 0. And remember that the potential energy difference is the difference between the energy that matters. It doesn't matter which path you take one point to the other. It's only the final minus initial that matters. So that means if you were to bring a positive charge all the way from infinity to this point, even though they will experience attraction and repulsion in the process of beginning, sometimes it is attractive, sometimes it is repulsive, but the net potential difference is going to be 0. So the point I'm making here, so we have V of A to be exactly 0 volts. Let's say V is at infinity. And V at B is also 0 volt because it's so far away. Like each observation point is very far away. So the potential difference between the two, VA minus VB, is equal to 0. Once the potential difference is 0, you can say that the potential energy, which is related to the work done to move a positive charge all the way from infinity to the center, will be equal to 0 because that's equal to the charge Q that you're moving times VA minus VB. Because energy was potential per unit charge, so you multiply by the charge, and since this is equal to 0, so that's equal to 0. But that's a very special case I have considered. That center point is the only point where you see that, or there might be some symmetric points here, but in general, if you were somewhere here, that's not the same. So the typical questions I ask is, if you were to move a positive charge all the way from infinity, so let us say somewhere 2 times length L here, then how much energy do you have to spend for that? Someone has to work on it. Someone has to exert that force, and you should be able to calculate that. And in your homework, you will do these problems, and I'll describe it when I'm making the solution. But here, I want to do another exercise. If we can bring in one charge, why not bring in more charges? Remember to move it. So that is a question in your homework where you have to assemble a set of charges. So the question typically asked is, how much energy, electric energy, let's say, electric energy do you have to spend to assemble three identical charges at the corners of an equilateral triangle. So the point we are making is, first think of an equilateral triangle. There are 3 points here. And the goal is to bring a positive charge all the way from infinity and keep it at the corner. So there is nothing here. There are no charges here to begin with. There is no other charge anywhere. So if you were to bring in a positive charge, it doesn't experience any force. So the first charge comes free of cost, right? Free of cost in the sense that there is no effort needed to bring in here. No one is going to repel that charge. So first positive charge on whichever corner you want, you can bring that here. So that's Q. There is no repulsion. It feels, so you're carrying this positive charge all the way from infinity. You don't feel any electric fields because there is no other positive charge repellent. Having said that, now you bring in the second positive charge, and your goal is to bring it here. But as you bring it here, this positive charge doesn't like the fact that there is a second positive charge coming closer, so it will try to repel it, and then that means you're pushing, right? You have to push this positive charge into this point, and then the question is, how much energy are you spending on that? And that's got by this energy, right? So it's Q1 times this, Q1 times this, but both are the same. So let's say this is 1 and that's Q2. So let's keep it different for a moment. So then the energy I have to spend, the first energy I'm spending is U12. And that is equal to whatever these positive charges are, is Q1, Q2, over the distance between them. So let's call it R12. If it is an equilateral triangle, all these lengths will be the same. If it is identical charges, all these charges would be identical. So that will be a simplification. If it was negative, one of them was negative, this will become negative. So that's for the first positive charge. Next comes the second, that's a third positive charge I have to bring in. And now you notice that this is not only repelled by this is also repelled by that. So when I'm bringing the third charge, it experiences 2 repulsions. So 2 contributions from energy. So that's U3, right? So this is U3, 1, and then there is U3, 2. That's your charge Q3. And this will be K Q3, Q1, over R31, the distance between these 2 points. So that's R31, R12, and that's R32. If it's an equilateral triangle, all these are equal sides. If they're identical charges, all these are identical charges. So otherwise, in general, these are different. And in fact, they can even be positive or negative. So how much total energy do you spend? The first time you brought in this, you have to spend this much. And the second time you have to bring in these two also. So the total will be equal to U12 plus U31 plus U32. If Q1 is equal to Q2 is equal to Q3, and if all the distances are the same, let's say the distance is length L, then all these three are the same, and U total only for an equilateral triangle is 3 times 3 because there is 1, 2, 3. It is not because there are 3 charges, it's because there are 3 interactions. If there are 3 objects, one can interact with 2, one can interact with 3, and 2 can interact with 3. There are 3 interactions, not because there are 3 charges. If there are 4 charges, for example, it's not 4 interactions, there will be 6 interactions possible. So think of a square. How many interactions possible? That's 1, that's 2, that's 3, that's 4, that's 5, and then that's 6. There's 6 interactions possible in a square for 4 charges, and that will lead to 6 interactions there. So this is KQ squared over L. And if we know the number L and Q squared, we can plug that in. I'll stop at this point. You should be able to do quite a number of homework problems now, and whatever is remaining, we will try to fill in the concepts on Monday. Thank you, and see you on Monday.